Good evening. Let me introduce myself. My name is Dvořák. I study theoretical computer science. I'm especially interested in theoretical computer science applied on problems in artificial intelligence, and I'm currently at the Institute of Science and Technology in Austria, Osterland. Today I wanted to speak about my current research, or my current efforts to do some research. And this area really lies in the intersection of theoretical computer science and artificial intelligence. We will study a large area of problems, which is usually denoted as CSP, which stands either for Constraint Satisfaction Programming or Constraint Satisfaction Problem. And what we care about is that we have a set of equations, or we have a set of inequalities, we can have a set of arbitrary conditions, and we want to know whether we can satisfy all of these conditions. That's basically a constraint satisfaction problem. And we can study which kinds of such sets of conditions are easy to check and which are hard. There are so many definitions of CSP, and I don't really want to dive into this definition. I just want to tell that CSP is a really large area, and most of the research in combinatorial optimization lies in some area of CSP, so it's like a really big buzzword, but I will mention only one specific type of CSPs called binary valued constraint satisfaction programming. Binary doesn't mean that we have variables of only two values. This is about functions we can use. We will work with binary functions. And VCSPs means value constraint satisfaction programming. So instead of just satisfying the conjunction of some conditions, we will be interested in minimizing some of functions or of expressions that can be minimums of other functions. I'm especially interested in one particular class of constraint satisfaction problems that's based on graph metrics. In fact, they should be called graph semi-metrics, but for some reasons we call them graph metrics. But let's start with a formal definition. We say that the function mean is a semi-metric on the set A if, and these will be axioms. First, for each element of the set, the distance between x and x is equal to 0. Mean is a distance function. We can write it as a function from the Cartesian product a times a to, let's say, non-negative real numbers. So first, everything is in 0 distance from itself. This is not an equivalence. I can have two distinct elements which have distance equal to 0. Second, for each x and y function f, the distance from x to y is equal to the distance from y to x. This is the classical symmetric condition which you know from ordinary matrix. And third is the famous triangle inequality. For each x, y, z from A, the distance from x to y plus the distance from y to z is greater or equal to the distance from y to z. Well, how can we imagine this? For example, consider Prague, Brno, and Ostrava. If we ask, what is the distance between Praha and Ostrava, defined as the length of the shortest path from Praha to Ostrava, this path must be shorter or equal to the sum of distances from Praha to Brno and from Brno to Ostrava. This can be equal. It can happen that the shortest path from Praha to Ostrava goes through Brno. Well, not in reality for these three cities, but in general we have this inequality. So, what can be a symmetry? For instance, consider the standard Hilbert space, the vector space, like let me say for general dimension, where we define a distance of two elements using the standard Cartesian product, I mean inner product. So it's the square root from sum over all dimensions xy minus yi squared. This is just a Pythagorean theorem, right? And if we define distances between points in R2 in this way, we can easily check that each point is in zero distance from itself. If we swap x and y, nothing changes. And we can also verify, I will not do it myself here, that the triangle inequality holds as well. In fact, this is a metric because this condition is if and only if, but we do not care about it. Every metric is a semi-metric as well. And now we need a second definition what an extension of a metric is. So, let y be a superset of x, that means that x is a subset of y, and me is a semi-metric on the smaller set, on set x. We say that m, first of all, we consider only semi-metrics. We say that semi-metric m this is me, it's on the smaller set, this is m, it's on the bigger set. We say that m, the semi-metric m, is an extension of me if and only if for each two elements in the smaller set of, I know the set is A, so I'm sorry, I will be an A. Could be more consistent. I'm sorry, me is a semi-metric of the smaller set A. Yes? Okay. For each x and y from the smaller set A, the distance defined by the original metric me is equal to the distance given by the new metric m, the new semi-metric. How can we understand that? We can add some other cities into our map, and none of the cities will create a shortcut between two cities which were present in the original map. Or if you like continuous mathematics, you can consider, for example, me being the distance metric for the two-dimensional Hilbert space, and n be the distance metric for some bigger nearby space. Let's say r to the power of 3. Now, this is always a symmetric. That's not a problem. This is satisfied, this is satisfied. We need to show that M is an extension of me. And in order to show that, we must show that for each AB in variables x1, for each x1 from r squared, the distance in r squared between x1 is the same as the newly defined distance using the semi-network M, which is true, of course, because if this was false, that would mean that we have a plane. There are two points or vectors, doesn't mind, x and y, and me measures the distance in the plane. M measures the distance using any shortest path in the whole space, and there would have to be a path from x to y which is shorter than the path that lies in the plane, which I will not prove, but it's really intuitive that this can't happen, right? So this was some continuous mathematics. Some people like continuous mathematics, but I specialize in discrete mathematics, yes?
So for example, if you had some plane in the 3D space, and you only had 2 points on the plane, and the shortest path between them was a metric, but if you consider the whole R3, then it wouldn't be an extension because you could go like this, like not on the 2D plane, which is bent.
You consider this. Oh, of course. Yeah. Or, for example, you can take a plane and you can glue edges and create a torus, and suddenly it's not an extension because there are still points that suddenly are closer to each other because they will use the boundary line, this point and this point. This point. Originally their distance was this, but now their distance is this, which is shorter.
Really,
Okay, so I will be interested only in metrics on finite sets, and a very convenient way how to define a semi-metric on a finite space is using the language of graph theory. We have some graph. Let's say it's a simple graph, and the distance between the vertices is the length of the shortest path between them. So, for example, distance from this to this is 1, distance from here to here is 2, distance from here to here is 3, and the distance from here to here is 4. Right. It's just a distance in the graph. Nothing complicated. We will consider a graph and its subgraph. Let me draw an example. And since now I will usually not write any formal definitions, so you better watch the pictures. To make it more interesting, I will not draw a tree. Okay, let's have a graph like this. The smaller graph will be.
Can I ask something? Like, it's not trivial. If you can define, like, every semi-metric on a finite set can be defined like a graph.
Not like a simple graph. Not like a simple graph. So right now we will be really limited only to simple graphs. I will make some generalizations later.
If I have a simple graph is like opposed to multigraph, or what does simple graph?
A simple graph means no multiple edges, no loops, and all weights are equal to 1.
Okay.
And no orientation. simplest thing we can define as a graph, right? This small graph will be called a template T, or maybe it's better to use T just for the sake of purposes of this graph. Let me call it H. And we will draw a bigger graph, H, with vertex P and edges E, and H will be a subgraph of G. H will be fixed, and G can be a part of the input. For example, G can look like this. Let me make something simple. And the part of that can be complicated, like this. Okay. And now, the distances in H are fixed. Now we have simple graph, so each edge has length 1. And we want to define the lengths of the red edges such that the symmetric in G will be an extension of the symmetric in H.
And that's a constraint.
Yeah, that's a constraint. So, for example, I have now I can use arbitrary non-negative numbers. So, for example, if I chose 1/4, 1/4, and 1/4, this is not consistent with the constraint because suddenly the distance of these two vertices will become strictly smaller than 1. And at the same time, I will be interested in a symmetric that minimizes some linear function. Let's say that we are asking about weight, or let's say weight, which is a function from e to non-negative real numbers, and now we will see why we can't call it a metric, because 0 will be sometimes included even for two separate vertices. And this is what we are searching for, and as a part of input we are given a vector of costs. Which has the same data type but different interpretation. For costs, there are no restrictions, and we are interested in W, such that the new graph metric will extend the old graph metric, and we will minimize this function. And for simplicity, now I will assign the same cost to all edges. So I am not going to write the costs, and I'm just asking you to define lengths of these red edges such that we don't create any shortcut with respect to the previous graph, and they are as short as possible in the sum. So for example, here, what is the smallest distance we can?
0.
0, exactly. If this is glued with this vertex, it doesn't create any shortcut in the previous graph. So for what about this vertex? What should be its distances?
It can't be 0.
It can have a distance 0 with 1.
It can be 0 on the middle?
Yes. Exactly, that will be optimal. And here, we basically
so it has to be 1 and 1.
Exactly. Here, it becomes a little bit tricky. What is the optimal solution?
The vertex when you are doing now, why don't we put there 1/2 to each line?
Oh yes. The distance 1/2, 1/2, and 1/2.
I meant like the one with ones and 1 0.
Because it would be shorter than the, yes, it would be shorter than the left way.
If we put like all those 3 lines from the vertex to 1/2.
1/2.
1/2. 1/2 instead of 0.
It will not work because the distance
Instead of 0, also 1/2.
it still doesn't work
Yeah.
because the distance of these two vertices was originally 2.
Okay.
And now
Yeah.
the distance
Now I
is
see.
down.
Yeah.
And moreover, this is more expensive than the correct solution. But I'm glad to ask. Do you see that this assignment is optional?
Yeah.
Okay. So this problem for a fixed template age is called the minimum extension problem. And each graph H is as a template induces one such an optimization problem, and we will be interested in its threshold decision variant. So basically we ask whether this sum, weighted sum, can be smaller or equal to some constant R specified as a part of the input. So this is the minimum extension problem.
So we are not asking for the solution, like for the optimal solution, but just whether it exists or not.
Yeah, but
There
if
is a solution better than something.
at least as good. So you see, I didn't solve this part. I don't know whether you can solve it by hand, but I can't. Okay, but we will formulate an algorithm that can solve such a problem. Well, we will not because it would take too long. Did you read the abstract of this lecture? It was called a minimum zero extension problem, but right now I have written only a minimum extension problem. For a minimum zero extension problem, we will have one more constraint, and this constraint will be that for each vertex V from the bigger graph G, there will be a vertex U in the small graph H, such that the distance between V and U is equal to 0. Looks strange, right? This basically means that we have to glue every red vertex to some white vertex, right? For example, this vertex is consistent with the condition because if this is V and this is U, we have a couple with distance 0. But this vertex is not consistent with this condition. If we were solving the zero extension problem, we would be supposed to glue this to one of these 3 vertices. And suddenly this worsens the solution, right?
So you're partitioning the vertices between the original ones and you're looking for the smallest multi-cut or something like that?
Smallest multi-terminal cut, yes.
Okay.
What is that?
We don't have to go into other equivalent definitions, but mathematical problems can be described in many different ways which are equivalent. So here, we have to choose arbitrarily one of the edges to have the length 0, so it goes here. And these 2 edges are forced to have distance 1. Can you see that? And this solution is worse than the previous one. Because here we had only 3 halves, and now we have some 2. And I'm asking, for a fixed template H and G and R being a part of an input. So this is an input, this is an input, and the function C is also a part of an input. How efficiently can I solve minimum extension problem, and how efficiently can I solve the minimum zero extension problem? If you know something about CSPs, you suddenly see that adding this constraint makes it a labeling problem. We basically want to label the big graphs using vertices in the small graph. But can you see, for some fixed page, some easy case of this problem? Some special, I will not show this. Just think about some template H such that the program is easier. Any ideas?
P has sufficiently few vertices.
But is sufficiently few.
Well, one is obvious.
Yes, it's obvious. What about two vertices?
Easy enough.
Yes. What is this problem equivalent to?
Oh.
Yes, it's the classical ST minimum cut problem. And we can
know what
solve
a minimal cut problem is. I know.
Okay, who here knows what a minimum cut is? Okay. Let me just say that I want to partition this whole big graph G into two parts such that one is connected to here, second is connected to here. And I'm forced to pay for each edge that connects these two parts because this edge has to have the length of 1. If it had a smaller length than 1, this distance will change. Okay, so we have a simple case. K2, and this can be solved in polynomial time by fourth-partial algorithm, for example. Can you see some hard instance of this problem? Case 3, exactly. If we have a triangle, this problem becomes equivalent to the three-terminal minimum cut problem, and this problem is going to be complete. So for K3, it is already complete. Quite a sharp transition, isn't it? Can it become even worse than NP complete?
No.
No, because
There is a certificate.
there's a certificate. Ah, exactly. This is just a labeling program, so I can give you the labeling and it will check it. Whether the labeling gives C times W small equal to R. Okay. So, what about K4?
Contains A3 as a minor.
Perfect. So it's minor is not sufficient because my next question is C4, and for C4 we can solve it in polynomial time. It's not easy, but we can.
Oh, right.
Jsem teď na druhý straně zanikání postavení a přednáška.
Do you have any other ideas what could be simple?
Even cycles?
Even cycles. No. For C6, this problem is NP complete. And I can show its NP completeness by a reduction from a max cut. If you know that the problem of minimum cut starts to be hard when we have 3 terminals, whereas the problem of maximum cut already starts to be hard with only 2 vertices. And the maximum cut problem is really convenient for proving NP hardness of many examples of minimum zero extreme problem. Path. A path. For path is simple.
Good.
You denote it by P5 or P6?
E6.
Okay, path on 6 vertices and can be solved in a polynomial time.
Okay. 3.
A 3! Great! Polynomial time.
There's a pattern.
Oh yes, there's a pattern. But before I will show you the answer, I would like to speak about the history of research on this problem. Let me open my timeline. Okay. Fourth and fourth. Proved that if the graph is a K2, then it can be solved in polynomial time. And this is a very result. 1955. Okay. More than 20 years later, Picard proved 1978. If it's a 3, then the minimum zero exclusion problem is polynomial solvable as well. Let's move another almost 20 years. that was showed in 1994 that if it's a complete graph on more than 2 vertices, then the problem is NP complete. It's equivalent to the multi-terminal card problem. Back then they didn't use this terminology. We do it retrospectively when we have this generalization of these card problems and all the crazy shit. And now we are finally getting to something that looks like a pretty neat characterization. It's year 1998, and Karzanov published a very influential paper saying several interesting things. If the graph is biverted, and at the same time the graph is orientable, and at the same time the graph is without isometric cycle of length greater than 5, then I should explain some terms.
Yes.
Okay. Biverted graph is a two-polarable graph. I mean, I can divide the vertices into 2 groups such that there are edges only between the 2 groups and there is no edge among vertices with a single corresponding to the same color. Orientable graph is a graph such that you can assign orientation to all C4 cycles such that the opposite edges have the opposing edges have the opposite orientation if you go along the cycle. For example, C4 is orientable. This graph is also orientable, but we are approaching K3. We can color it like this and this. This graph is not oriented. Do you want to see much struggle? It takes a long time. The problem is that each of these edges is in several cycles of length 4 and they become somehow inconsistent. It's not easy to see this.
Okay.
I would like to move on because I have only 12 minutes, so I can show you the state-of-the-art results.
And what's the without isolation?
Yeah, I'm saying that this graph cannot contain an isometric cycle of length greater than 5. So, for example, this is an isometric cycle of length 6. This is also an isometric cycle of length 6. But this is not an isometric cycle of length 6 because the distance in the cycle does not correspond to the distance in the whole graph. It's basically a cycle without shortcuts. It's something similar to the notion of external.
So if every edge had a sign value of 1, then this should be an extension metric on the
cycle. Exactly. But this has an isometric cycle of length 5, which makes it a bipartite graph, which makes it a graph which cannot be bipartite. So we have no proof of being solvable in polynomial time. Perfect. Okay, Karzanov proved several other results. If the graph is hereditary modular, and at the same time the graph is orientable, then the problem can be solved in polynomial time. The modular graph is a graph that for each triple of vertices the interval of each couple intersects at some point, where interval is a set of all vertices that lie on any shortest path between the two vertices. So, for example, a regular grid is a modular graph because if I choose any three vertices like this, this and this, I can always find a vertex which lies in the intersection of all three intervals because I can choose the middle, the median like x and y. So this is in the middle, this is in the middle, and this vertex must be in all three intervals. Basically, the interval of these two vertices is this rectangle, right? Equivalent formulation is that for all three vertices, I can choose a fourth vertex, such that this fourth vertex can be set as a middle point common for all three paths, and neither of them becomes longer than it previously was. And the graph is hereditary modular if the graph is modular and each of its isometric subgraphs is also a modular graph. This is maybe too abstract, but we will mention simpler characterizations of these graphs. Karzanov knew that if a graph is bipartite and orientable and doesn't have two long cycle, then the graph also has these properties and vice versa. Yes?
So isometric means subgraph maintaining the shortest path metric.
Exactly.
Good.
At the same time, Karzanov proved some negative results. And now it's becoming really interesting because we are almost in the case of a complete characterization, which, by the way, we have a constraint satisfaction.
If you're searching for this,
by the way, if we have a constraint satisfaction problem with a fixed language, which means that the functions we can use are not a part of the input, but they are fixed. We have the famous dichotomy theorem that says that such a language is never NP intermediate. If we assume that P is not equal to NP, then the CSP problem can either be in P or it can be NP complete, but it cannot be anything in the middle. It's quite a new result, yes. And it's very exciting. Karzanov also proved that if the graph is non-modular, then the problem is incomplete. It's basically a generalization of the Dalhouse result. Because K3 gives us an incomplete problem. And now Karzanov proved that this problem is incomplete for any non-modular graph. And also he proved that if the graph is not orientable, then the problem is also incomplete. It almost looks like a complete characterization, but we still have some doubt. What if the graph is modular, but not hereditarily modular, and it is orientable? Now we don't know whether it is in P or whether it's complete. We don't know it can be in the middle, but we don't know which of these two extremes we are meeting. So, Hiroshi Hirai comes into the scene, and this Japanese scientist proved in 2012 that if the graph is modular and orientable at the same time, then the problem is solvable in polynomial time. So this result is stronger than this result. And suddenly, we have a complete characterization of graphs with respect to the minimum zero extension problem. Because if the graph is orientable and modular, we have a polynomial time algorithm which is based on linear programming relaxation techniques. And if it's non-modular or non-orientable, we have the proof of incompleteness. And when I mentioned linear relaxation programming technique, we basically speak about solving the minimum extension problem and claiming that the solution to the minimum extension problem is equal to the solution of the minimum zero extension problem. By the way, if you want to construct the linear program that solves the minimum extension problem, you can get into trouble, because if you want to express the conditions of being a semi-metric extension, you can end up with exponentially many conditions. So it can be done in the most straightforward way. However, there is a solution which uses only a polynomial size subset of these conditions and makes polynomial number of calls to our linear programming library and gives us the solution to the minimum extension problem. And for several classes of graphs, we know that the solution to the minimum extension problem is equal to the solution to the minimum zero extension problem. And we are almost in the present moment in it was the year 2014. Again, Hirai published a very slight modification of his algorithm, and he proved that if the graph is weighted modular, and orientable, then it can be solved in polynomial time. He proved it for weighted graphs, and now we consider modularity in the weighted sense. This problem also, of course, this problem contains all the unweighted graphs, but this result is stronger because the template is not part of the input. It can happen that this problem is suddenly simple or harder, you don't know. But he proved it for weighted modular graphs. And we have last two results I want to mention. 2017 proved about this very general class of CSP problems, the dichotomy theorem I was briefly mentioning, that for fixed language the CSP is either in B or it is incomplete but nothing in between. And now we have here 2019, and Dvořák proved the part of the negative result complementary to this, and he showed that if the graph is weighted non-modular, then the problem is ended. So this was a brief history of the minimal zero extension problem. Do you have any questions? Okay, that's all from me. Enjoy the rest of the class.